And ladies and gentlemen, we're ready to start the next section of calculus. Now, for those gentlemen in the class that don't exactly know how to approach that special young lady, might I suggest this cartoon? Quite clever and quite nerdy all at the same time. So read it if you'd like, pause the video, otherwise we go on. Alright, 10-2 vectors in the plane. Now, majority of this lesson, a little more than half of this lesson, is going to be just a reflection upon the things that I taught you about vectors in pre-cal. We'll talk about two-dimensional vectors, we'll do the vector operations, we'll do motion with vectors, but then we'll apply the calculus and we'll look at velocity, acceleration, and speed with vectors and displacement and distance traveled. Alright, two-dimensional vectors. Now, certainly you'll want to pause the video and read this, but really it's nothing more than just things that you had learned last year about vectors. Vectors, of course, is a specific location in space, has a direction, has magnitude, and we can represent it in component form right here if it begins at the origin 0, 0. The magnitude is the amount of the vector or the length of the vector, or we can say the absolute value of the vector, and is oftentimes given by the absolute value bars. If you are in component form AB, the magnitude is simply radical A squared plus B squared. Again, all of this stuff you will find in your pre-calculus notes. If you do not have what we would call the component form, you can put a vector in component form by doing the HMT rule, head minus tails. You do the terminal point minus the initial point. Again, see your pre-cal notes if you want further examples. Example 1, finding magnitude and direction. Our job is to find the magnitude and directional angle of this vector here. So how long is this blue line, and measuring from the positive x-axis, what is this angle right here? We start with the magnitude, radical A squared plus B squared. Certainly nothing real difficult about this. That's going to be 1 plus 3 is 4, which the square root of 4 is 2. So if you were to take out a ruler and measure that, that is going to be 2 units long. To find the angle, we do arctangent. Now the reason we do arctangent is if you can imagine a line coming down here, this makes a right triangle, and the opposite side, which is radical 3, is here. The adjacent side, which is negative 1, is here, and of course tangent is opposite over adjacent. So we plug in our B and our A. It's the arctangent of radical 3 over negative 1, which is negative radical 3. And that gives me 2 pi over 3. Now technically what that would give me is just pi over 3. But pi over 3 would assume a first quadrant answer, or negative pi over 3 would assume a fourth quadrant answer. But it's very clear that this is in the second quadrant. So I get that 2 pi over 3 from the unit circle in the second quadrant. Alright, finding component form. Now, finding component form if you're given points is one thing. Finding component form if you're given a magnitude and a direction, something different, but still not difficult. The component form given magnitude and directional angle is r cosine theta, r sine theta. So for this problem, r is going to be 3, and the theta is 40 degrees, and we get that right there. Now, again, this is certainly not an angle that's on the unit circle. Were it on the unit circle, I would expect an exact answer with radicals or fractions. But as this is not on the unit circle, decimal approximations are fine, and 3 decimal places is probably a good amount. Vector addition and scalar multiplication. Again, simple stuff from pre-cal. If you want to add vectors together, simply take the first and the first, add them together. Second and the second, add those together. Hopefully you remember that. Scalar multiplication, if you have a number on the outside, say you want to double the magnitude of a vector or triple it or by half, you just take that number that's on the outside and you multiply it through. Opposite of a vector is just change the sign of all the vectors. Make all the vectors or numbers negative or positive or just whatever the opposite of what they were. So, ladies and gentlemen, I give you vector u and vector v, and I ask you to find these 3 things. Now, you probably can do this from pre-cal, but go ahead and pause the video if you want to try it yourself. But here's my solution. 2u plus 3v. I'll take the u vector, negative 1, 3, multiply by 2. I'll take the v vector, multiply by 3, and I'll add them together. So 2u, 3v, 2u, 3v. Now, you may not like this format, You may prefer just to do multiply 2 by u completely, multiply v by 3 completely, and then add. However you want to do it is fine. But regardless, when I multiply them, when I add, I get 1027. U minus v, first of u minus first of v, second of u minus second of v. And we simplify that down to -5, -4. Half of u, but notice it's not just half of u, it's half the u magnitude. So I take half of u, -1, half is -1/2. Half of 3 is 3/2, and I'm doing magnitude, so square root of a squared plus b squared. And so that's 1/4 plus 9/4, which is 10/4, radical 10 over 2. And here are some properties of vectors. You probably knew these already. Vectors are commutative here. They are associative. They do follow the additive identity rule. They also follow the additive inverse rule. 0 vector times any vector is 0. 1, a scalar of 1 times any vector is the same vector. Common sense. If you're multiplying 3 vectors together, or I'm sorry, 2 vectors or 2 scalars and a vector together, you can either do scalar 1 through times then scalar 2, or you can multiply the scalars and then multiply the vector. It does not matter. If you're doing a scalar times vector, the distributive property applies, whether it's here or if it's 2 scalars added together in a vector. Again, distributive property applies. And now our next slide, ladies and gentlemen. An airplane flies 500 miles per hour due east, encounters a 70-mile wind that acts at a direction of 60 degrees north of east. Our job is to find the new speed, or velocity if you will, and direction of the angle. So our job here is to take each of these situations, the airplane and the wind, and create a vector out of it and then add them together. Well, we'll start with the airplane. That's easy. We're going due east, which if you look at due east here, you know that's at 0 degrees or 0 radians. And we know it's at 500 miles per hour. The wind is at 70 miles per hour, and it's acting at an angle measure of 60 degrees. And remember, just a slide or two back, r cosine theta, r sine theta. Now we know that cosine of 60 is 1/2, sine of 60 is radical 3 over 2, so we simplify that, and then we add our 2 vectors together. Now we can't stop here. This is the component vector form of the answer. We want the magnitude and direction. So we take that vector and we find the magnitude. Radical a squared plus b squared gives us a new velocity of 538 miles per hour. And we take that same component vector, arctangent of b over a, and we get an angle measure of about 6.5 degrees north of the east. So this little angle right here, about 6.5 degrees. The length here, 538. Alright, now let's do some calculus. A particle moves in the plane, so its position at any point in time, non-negative that is given by sine of t and t squared over 2. Our first job is to find the position vector. Now again, this here just represents a location, just like an xy coordinate point, if you will. Well, the position vector is just that point. That's very simple. The point describes location, position describes location, so there we go. Now to find the velocity, I just remember from weeks past, the velocity is simply the derivative of position. So I take the derivative of sine, I take the derivative of t squared over 2, and I get cosine and t, and that is the velocity vector. And then I remember that acceleration is also the derivative of velocity, so I'll take the derivative of cosine, and I'll take the derivative of t, and I have negative sine t. So here, ladies and gentlemen, is position, there's velocity, there's acceleration. When we're dealing with vectors, we follow many of the same rules of derivatives. Alright, velocity, speed, acceleration, and direction. And what I just demonstrated in the last slide, that's what all of this is. If you have a vector, a situation where the position can be described by any point x, t, y, t, then that is the position vector. Derivative is velocity, second derivative is acceleration. Alright, a particle moves in a plane with a position vector given below, which is right there. Find the velocity and acceleration. So if you want to pause the video now, that's fine. Just remember, first derivative is velocity, second is acceleration. Now, if you didn't pause it, or if you've already paused it and worked it, let's go ahead and continue. To find the velocity, we'll do the derivative. The derivative of sine is cosine, but don't forget the derivative of the inside by the chain rule is 3. And the derivative of cosine here is negative sine, and again, chain rule, the derivative of 5t is negative 5. There's velocity. Now to find acceleration, we'll take the derivative of velocity. The derivative of cosine is negative sine, but again, the chain rule, I'm going to need another 3 out front. And so I have this. And the derivative of sine is cosine, and I need another 5 out front by the chain rule, so that gives me negative 25 there. Now, if we were to sketch this position, just to give you an idea of what's coming, if you were to take the position functions as we had them earlier and sketch them, this is the graph that you would get on your calculator. By all means, give it a try. You will have to be in parametric graphing because you see xt, yt, so it is parametric to sketch this graph. It's pretty crazy, and we're going to actually sketch things that are even crazier than this as we go through this section and do the homework. Alright, next problem. A particle moves in an elliptical path given by this. We're going to find velocity and acceleration vectors. Then we'll find velocity, acceleration, and speed and direction of motion at t equals pi over 4. So we're going to do a lot of stuff at pi over 4. Then we're going to sketch the path of the particle. So we're going to have a graph showing, ladies and gentlemen, showing the velocity vector at the point 4, 0. And then we're going to decide if it travels in a clockwise or counterclockwise direction. So a lot of stuff to do here. Alright, we'll start with the velocity. The velocity, again, is just a derivative of position. Position would be this, just in vector form. So derivative of sine is cosine. The derivative of cosine is negative sine. There's our velocity vector. Acceleration vector, the derivative of cosine is negative sine. The derivative of sine is just cosine. So that's simple. Now the next thing asks us to find all these things at pi over 4. So we'll do cosine of pi over 4 here for velocity, sine pi over 4. We know that cosine and sine both at pi over 4 are radical 2 over 2. And do the same thing for acceleration. Radical 2 over 2 times 4 is this, and times negative 2 is that. Radical 2 over 2 times negative 4 is that, negative 2 radical 2, and times negative 2 is this. So very simple stuff, just using the unit circle. The position, ladies and gentlemen, the position of the motion is this right here. Now, how do I get that? Well, I just simply take the originals and I make that sketch. Now, at 4, 0, I have a tangent line 0, negative 2. Now, you may wonder how I got that. So here's what I did. I asked myself the question, what value of t could I plug in that produces 4, 0? Because this is the position right here, 4, 0. Well, I knew that I wanted to keep the 4, so this had to be 1. So I thought about to myself, what makes sine equal to 1? Well, what makes sine 1 pi over 2 makes sine 1. So if I plugged in pi over 2 here, that gives me 4. And if I plug in pi over 2 for cosine, it gives me 0. Now, to get this answer right here, I take that pi over 2 and I go back to my velocity function here. And if I plug this in here, pi over 2 gives me 0. And pi over 2 here gives me negative 2. And so that's how I came up with this. Now, this vector is pointing down here, which would suggest that it's going to keep going in this direction right here, which is, in fact, a clockwise motion. Alright, displacement and distance. If you are given a vector and you want the displacement, again, displacement is just change of position. It's not total distance traveled from A to B. You simply take the integral from A to B of the velocity, of the first part, of the velocity that is, and then do the same thing for the second part of the velocity. If you want the distance traveled, we take the square root of, and then you see here, this is like doing the magnitude. It's the first part of the velocity squared plus second part of the velocity squared. So displacement, we just do the integral of each individual part, and total distance traveled, we find the magnitude, and then we take the integral from starting to ending position. Ladies and gentlemen, I'm about at the 15-minute mark, so I'm going to have to stop this video, and we'll just have just a couple minutes left for the next video to finish up.